After discussing nuclear magnetic resonance spectroscopy, like these all analytical techniques, this is also the next technique that we have to discuss. Basically, what the chromatography does, it's the separation and also the purification technique. Through this technique, we can separate as well. Through this technique, we can find out the purity of a compound as well. Remember. So, and also this is not the new topic for you. We'd also discuss this topic in O levels or IGCSE. So, separation technique in which components are separated because of different interaction with mobile phase and stationary phase. So now you can see the new word, that is mobile phase and stationary phase. What is this? Mobile phase and stationary phase. So basically, uh, let me tell you first thing, what is mobile phase? Mobile phase that can move. Mobile phase means that can move, liquid or gas. It may be liquid, it may be gas. Mobile phase can be liquid, it can be gas that flows through chromatogram, moving the components to be separated at different rates over a stationary phase. Let's say, hopefully, you know the paper chromatography in which we used to use water as a solvent and we used to dip a paper into the water. So the water was acting as a mobile phase and the paper was a stationary phase, isn't it? And we used to apply black ink, like the dot of black ink on the center of the filter paper. And the black ink started to move into three different or four different or two different colors on the basis of their solubility. And we have decided, like we saw that, yeah, that color is separated into different components. So then we uh, then we knew that, like, the black color is not a pure color, but it's the combination of two or three different colors. So how did we know this concept? After doing chromatography, we have separated this color into different components. So that's what we used to do in past, isn't it? So I want to say the mobile phase was a liquid, like the water in that case. And the filter paper was stationary phase. Like stationary phase doesn't move. On the stationary phase, we apply our sample. Like in this case, the sample is black ink, the dot of black ink that I want to separate it. Or when I dip that filter paper into the solvent, that is mobile phase, then the sample is started to separate into different components on the basis of different solubility. Hopefully you are getting what I'm trying to say, what is mean by the term mobile phase or stationary phase. So mobile means moving. Then stationary phase, the phase over which the mobile phase passes. The phase over which the mobile phase passes. Like, I mean to say, this is the paper and I have applied a black ink on that, and the ink is separated into different colors. It's red, it's yellow, it's blue. So basically, on that filter paper that is called stationary phase, I have dipped this paper into the water. The water is acting as a mobile phase. When the water goes up like that, when the water goes up like that, so the components are separated into, like, the sample is separated into different components. That's what we do in chromatography, right? So you need to know the difference between mobile phase and stationary phase, right? Then we will be looking at the two types of chromatography, that is adsorption chromatography and partition chromatography. Adsorption and partition. So we need to look at these two chromatographies, adsorption and partition. Let me tell you what is adsorption. When stationary phase is solid, that is called adsorption chromatography. What? When the stationary phase is solid. And when the stationary phase is liquid, it's going to be partition chromatography, right? So this is to be very clear, crystal clear. You need to know this. What is the difference between adsorption chromatography and partition chromatography? So in adsorption, the stationary phase is going to be solid, and in partition, the stationary phase is going to be liquid, right? So after looking at this, we are going to discuss paper chromatography. What the paper chromatography is, what we do in this chromatography, stationary phase is water. Let me tell you how a stationary phase is water. And a mobile phase is hexane. Mobile phase is what? Hexane. And we know that water is polar and hexane is non-polar. Water is polar and hexane is non-polar, right? Why water is polar? It's a different, like I can say, debate. On the basis of the difference in electronegativity, we generally decide why the things are polar and why the things are non-polar. You know, in water, hydrogen and oxygen both are different, having different electronegativities. I would say this is going to be polar. And in hexane, it's going to be carbon and hydrogen. It's a hydrocarbon. You know, all hydrocarbons are non-polar. So, you can see what I'm doing. This paper is made of cellulose, isn't it? This paper is made of cellulose. It's a simple filter paper. It's a simple filter paper, right? Made of cellulose. In the cellulose, we have small pores. You know, we have what? Small pores. In that pores, there is a water molecule. Water molecule is hidden inside the pores of that cellulose paper. So that's why I'm saying this is a stationary phase. It's not moving. So I have dipped that paper into hexane. That is organic solvent. It's non-polar solvent, right? So, and then I have applied a sample onto it. It may be blacking, it may be any other dot, it may be any other sample that I want to separate it, you know, through the chromatography. So, in this, the stationary phase is liquid. It's a partition chromatography. It's not adsorption, by the way. Okay, it's partition chromatography, right? So why? Because the stationary phase is going to be liquid. That is water. Okay, that is water. Okay, right? So in this way, we can determine like what type of chromatography is this? Is this adsorption or is this like partition chromatography, right? And then uh, the components are separated into A and B. A is yellow color and B is blue. B for blue, like sorry. We have two components A and B. A is yellow and B is blue, right? Now I can say A has traveled more distance, isn't it? If this is my reference line, I'm going to measure each and everything through this line. So A has traveled more. Let's say is 4.5 centimeter and B has traveled less is 2.5 centimeter. On the basis of distance, I'm saying A has traveled more than B. Why? Because it has more affinity towards the solvent. You know, water was a mobile phase, isn't it? Water was a mobile phase. Water was a mobile phase. And water was polar. So if the sample is moving, if the sample is traveling more, if the sample, listen carefully, if the sample is traveling more, if the sample is traveling more, it's mean that it has a greater affinity. It's mean that it has a greater affinity, isn't it, towards the solvent. That's why it is moving with that solvent, right? So let's say B has a lower affinity with the solvent. That's why it didn't move with the solvent. It didn't travel so much with the solvent because it has a lower affinity. So on the basis of the distance, we can decide. On the basis of the distance, we can decide which component has a greater affinity and which component has a lower affinity with that solvent. So on the basis of distance, we can decide. And this is going to be very important, right? So we can tell about we can predict the force of attraction between the two components on the basis of that distance, isn't it? So we need to know this. And before going to describe this, we must know the polar and the non-polar part. We must know the polar and the non-polar part, right? Let's say I told you that water is polar and hexane is non-polar, isn't it? So if A is traveling more, if A is traveling more, so means that it has a greater affinity towards the solvent. And what was the solvent? The non-polar one. So I can say, right, A has more non-polar nature, isn't it? Because it has a greater attraction towards the solvent, and the solvent is going to be non-polar. So I can predict that A is going to be non-polar, isn't it? And let's talk about B. B has traveled less distance with the solvent, and we know that the solvent is non-polar. So the nature of B is going to be polar, because we know the concept polar dissolves in polar and non-polar dissolves in non-polar. For the solubility, the nature should be the same. Why sodium chloride is soluble in water? Because both are polar. Sodium chloride is also polar and water is also polar. So both are polar. That's why they are soluble in each other. Isn't it? If hexane is non-polar, right? If hexane is non-polar, so A is traveling more distance. A is traveling more distance. It means that the nature of A is going to be the same, just like hexane. Like I can say A is also non-polar, right? So in this way, indirectly, we can take an idea about the polarity of that substance, whether the substance is polar and whether the substance is non-polar. So what I'm taking an idea after looking at the distance. So distance is having very important role on the polarity. Okay. And then uh, we have different type of chromatography, right? Sorry. Like I am explaining over there that this is going to be partition. I told you that why this is partition, why not adsorption? Because the stationary phase is liquid, right? And also we have to find out the RF value. What is RF value? Basically, this is going to be uh, distance traveled by spot divided by the distance traveled by the solvent. Like you are saying that the sample has separated into two different components. But how can I justify this on the basis of exact values? So the value is RF value. If you have one RF value, so means that the sample is separated into only one category. The sample is separated into one category. And if we have two RF values, so means that the sample is separated into two different categories. And if we have three RF values, so means that the sample is separated into three different categories. So based on the RF value, how many RF values we have? Okay. So what is the formula for RF value? Distance traveled by spot divided by distance traveled by the solvent, right? So no unit of RF value. Why? Because this is the ratio between the two same values. Numerator, it's distance. Denominator, it's distance. If you are measuring the distance in centimeter and centimeter, so centimeter and centimeter, they are cancelled. If you are taking the distance in meters, they are cancelled. So this is the ratio between the same values. That's why there is no unit of RF value. Remember, it's very easy. Okay. And remember also the value of Like the RF value should not be greater than 1. It should always be less than 1. It should always be, the RF value should always be less than 1. Remember. Okay. So, and how can I measure the RF value? This is called solvent front. This is called solvent. What is solvent front? Distance traveled by the solvent. What is distance traveled by the solvent is called solvent front. Let's suppose I'm going to measure the RF value. I'm going to measure the RF value. So what I'm going to do? I'm going to take a ruler like that. Okay. And okay, then I can say it's going to be 0. Then it's going to be 1.1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 2. And this is going to be 2.9 centimeter. Isn't it? The distance of the solvent front through this line, the baseline, is going to be 2.9 centimeter. So what is 2.9? It's the distance traveled by the solvent. And let's suppose if I want to measure the distance of spot A. If I want to measure the distance of spot A, it's going to be, we always take the center of the spot. So it's going to be what? 1.9 around, isn't it? So 2.9 and 1.9. So how can I find RF values? Since we know the formula of RF, distance traveled by the spot divided by distance traveled by the solvent is going to be your RF value. In this way, you can calculate each and every RF value through this. Okay, it's not new for you. Again, I'm saying because you did already in the previous classes, so you can just get small revision. So what I did, I found the RF value for the yellow spot. I found the RF value for the red spot, green spot. And then right now I have two RF values. I got the two different RF values. I got the two different RF values, remember, right? Okay. So, so now I can say that, okay. And you can see this is going to be 0.003 and this is going to be 0.03. So this RF value is smaller. If this is smaller, spot has greater interaction with the stationary phase. If the RF value is smaller, isn't it? Spot has greater interaction with the stationary phase because it didn't move with the mobile phase. If the substance is not moving with a mobile phase, what does it mean? Listen carefully. If the substance is not moving with a mobile phase, what does it mean? It has a stronger interaction with the stationary phase. It has a stronger interaction with the stationary phase. That's what I'm saying. And the RF value for the yellow spot is going to be 0.03, which is bigger value, which is bigger value, right? Which is bigger value. So if this is going to be bigger value, means that it has a more interaction with a mobile phase because it has traveled more. Because it has traveled more. Isn't it right? So on the basis of RF value, on the basis of RF value, you can also decide. What I'm saying, on the basis of RF value, you can also decide, remember, you can also decide the interaction of that substance with the solvent and also interaction of that substance with the stationary phase, like with both, with mobile phase as well, with stationary phase as well. Okay, then Let's move on towards the next topic, that is going to be TLC. What is this? TLC. It's thin layer chromatography. It's thin layer chromatography, right? Thin layer chromatography. So what is this? It's quite similar to paper chromatography when we have used filter paper for the chromatography, right? It's the same. It's the same. Almost it's the same, right? So I can say that in this chromatography, what we are going to do, we are going to take a paper that is coated with silica. It's called TLC paper. What is this? It's called TLC paper. So through this TLC paper, the results of the chromatography would be very much accurate. Remember, through this chromatography, like through this paper, when you are using TLC paper, the results would be very clear, would be very accurate. So that's why it's more recommended. Like the TLC is more recommended, right? So, and by the way, let me tell you, this is not partition chromatography as the paper chromatography was. No, this is going to be adsorption chromatography. What is this? This is going to be adsorption chromatography, right? So, you know why? Because it's paper coated with silica. Silica is solid. What I told you, when the mobile phase is solid. What I told you, when the mobile phase is solid. So I would say that this is adsorption chromatography. Okay, this is adsorption chromatography. So silica and sometimes it is alumina, 100% coating. Very fine particles are coated, very fine particles are applied on that paper, right? Even when you will touch the paper, you will feel that some powder is being like I can say becomes non-sticky because you know the particles are sticked on that paper. So when you will touch the paper, so you will see that some particles are moving from their place, some particles are leaving that paper. So this is very fine particles, or I can say that then I did the same thing. I took the same substance, I took the same sample, I took the same solvent, I took each and everything same, right? I took each and everything same. So what's the difference between the normal chromatography, like the paper chromatography, and this TLC? Only the results. Only the results. This is going to be more accurate. Only the results. Okay. Nothing is changed. Everything is same. RF value is same. Procedure is same. Everything is same. Only this is more accurate. Let's suppose if you are going to take a picture with a normal phone, like let's say local phone. And on the other hand, if you are going to take a picture with iPhone 16 Pro Max, 17 Pro Max, so the results would be very clear, isn't it? The results would be very clear. So, yep, I can say that this is going to give you the more accurate results. Like I was separating something else using paper chromatography, but I didn't see any positive result. So then I have decided that I need to do something different, something else, so that using another chromatography, I can have the more accurate results. So I am supposed to do TLC, like thin layer chromatography, right? So I'm supposed to use thin layer chromatography. Okay. So this is thin layer chromatography. And also, uh, you can see uh, what I'm doing over there. You can see, you know, sometime we see that the components are not separated into, like you can see, the two colors are even like still mixed. They are not separated using the TLC, like the thin layer chromatography. So what we are supposed to do in that case? This is very important topic. Remember, this is going to be another topic, that is two-way chromatography. Two-way chromatography. So what is two-way and one-way chromatography? If the substance, the sample, is not getting separated from each other in this method, so then just what we can do, just rotate the paper to 90 degrees. I did the same thing. After rotating the paper, when I have dipped that paper into another solvent, then the components are separated, isn't it? So that's the advantage of using the two-way chromatography. If the sample is not separated using one-way chromatography, so then we can use the two-way chromatography. Remember, this is the advantage of using two-way. Okay. In only case when the substance are not separated, still the substances are not separated from each other. So then we are supposed to use two-way chromatography. Remember. Okay. Hopefully this is very clear. Okay. Then we have another chromatography that is known as column chromatography. That is known as column chromatography. So in column chromatography, yeah, I can say this is going to be, the purpose of doing chromatography is the same. Remember, this is very important. The purpose of doing chromatography is the same, right? So when we are doing column chromatography and when we are doing um, simple paper chromatography, when we are doing TLC like the thin layer chromatography, so the nature of doing this all is same. Like we are separating and we are purifying. Remember, the things are same. Only the difference is some are accurate and some are not accurate. That's it. That's the only difference. Remember. Okay. So in column chromatography, you can see stationary phase is again silica, column packed with silica. And then we are passing the sample. Sample is liquid, of course, into that column, right? Sample is passing through that column. Column is long. So when the sample is passing through that column packed with silica, so some components will travel faster, just like this blue, and some components will not travel faster. Why? Let's suppose if the component is traveling faster, I can say it has a greater affinity towards the solvent. If this component is not traveling faster, still it's here. It means that it has a greater affinity towards the stationary phase. It has a greater affinity towards the stationary phase. Okay. So this is quite fast method because it's towards the gravity. The solvent will move faster. Components are isolated, like separated easily as compared to when you are doing TLC. And time taken for a component to pass through the column is, again, you will see this is going to be more faster, isn't it? This is going to be more faster, right? So in this way, in this way, we can do column chromatography, right? So everything is same, by the way. When you will see after that, I'm going to send you the notes as well. So then you will feel that they all are same, but the small things are going to be different, right? बाकी चीजें मिक्स हो जाएंगी. मैं I don't want to start G